Okay, so let's go ahead and get started. Our next presentation is with Simula, Tor Skeie.
Okay, my name is Tor Skeie, I'm from Simula Research Laboratory in Norway, and I'm going to talk about factories and dragonflies and compare them from scalability, cost, and blocking perspective. The dragonfly has been proposed as to be a very cost-efficient solution for building large-scale networks. There is, however, I would say a general lack of a thorough evaluation of the dragonfly. So, and that's why we have conducted a study on it, and that I'm now going to summarize for you. Before I begin, I would just like to make some acknowledgements for the guys who have been involved in this work here, and those are Frank Olav Sem Jacobsen, Sven Arne Reinemo, and Matthias Muland, colleagues from Simula, and Aitan Sahavi and Gilad Scheiner, both from Malnox. Now, for the agenda, I would like to start with some motivation before continuing with discussing the characteristics of the factory, and then I will dive into the dragonfly topology, how to build this topology, and the thoughts behind it. It's so that the dragonfly is a hierarchical topology, and it consists of a number of groups of virtual routers that have their own internal network, and I will also discuss about suitable topologies for this internal network. And then to the essence, presenting the blocking and the cost and the scalability characteristics, comparing Dragonfly then with the factory. And finally I will conclude. It's a well-known fact that the factory is the most used topology for InfiniBand networks. I think it was in 2008, 2009, the Dragonfly was proposed then to be a very cost-efficient topology for large-scale networks. There are some papers published on Dragonfly, and even one of several of them will even compare with the factory. But I would say this comparison is somehow limited and it's not fair in every respect. So that's the reason why we have done this work, and where we would like to answer the following questions. That is the Dragonfly really a viable alternative to the factory, and actually how competitive is it? And how do they compare in fundamental properties such as blocking and scalability, and not least, what about the cost? And what are attractive Dragonfly configurations? And here in particular, I have the group topology in mind. Let's start off with the factory, and as already said, it is the most common InfiniBand topology for InfiniBand, and that's simply because it holds a number of attractive and important properties. And as for instance, the routing in it is trivial. It's just to route upward in the tree, and then followed by downward in the tree to reach the destination. And so no virtual channels are required for deadlock avoidance. And it also offers path diversity, so it also holds fault tolerant properties. Further, it also offers full bisection bandwidth for arbitrary permutations. So if actually it's also rearrangeable non-blocking. So if the number of input links and output links is equal for each stage in the tree, it's rearrangeable non-blocking. And if it gets narrower towards the root, it is oversubscribed, and if it's wider towards the root, it's actually over-provisioned. So these properties actually makes the Dragonfly, no, excuse me, the fat tree easily adaptable to traffic requirements defined by the applications or the network. It's also scalable in cost, as we will see in a minute. One downside is, however, that the performance might suffer slightly due to static or oblivious routing. When building a factory, not only the switches can be the building blocks, but also larger integrated circuits, as shown here. And here we are actually illustrated a 3-level factory, where the first level here is made up of 36 port switches, but where the two topmost tiers have been integrated into multiple chassis, where each of them then implement 648 port switch. So made up of then implemented then as a 2-level factory. And that's a very cost-efficient way of building factory, because you get rid of a lot of cables. The links are simply integrated into the chassis. So then to the Dragonfly. It has been proposed by John Kim, Bill Daly, and some colleagues, and then to be a very cost-efficient topology for large-scale networking. And it has caused some discussion in the HPC community whether it's suitable for InfiniBand and if it could be on exascale topology. It's as already said, it's a hierarchical topology, and it have the following properties. It consists of a number of groups, and there is a all-to-all link connection between the groups. So, and that means that each group at least have one direct link to each other group. And about the topology inside the group. Here we see the groups, all the groups. We have just illustrated all the groups around this border. If you now look at the inside the group, the topology can actually be of any topology, but it's recommended. But it's flattened butterfly that is recommended. The issue here is to reduce the network diameter as well as reduce the number of long links. But bear in mind that the Dragonfly requires non-minimal adapter routing and even further also advanced congestion look-ahead functionality for efficient or optimal operation. And that also makes the back pressure mechanism more aggressive. Let us then go a bit more into detail. We here have the groups that then are connected by an intergroup topology, and about the groups. They also will consist of a number of switches here that is also connected by a group topology. According to the definition of the Dragonfly, each group will consist of A switches, and each of the switches has P terminals connected to it, as well as H global links. So those global links are then used for connecting the groups. And and the global links or the long links here will be fiber-based, and the local links will be electrical. So the important issue here is, of course, to fully utilize the costly or the fiber-based links. Since non-minimal adaptive routing will be used between the groups, it means that most of the traffic between the groups will cross two links. First, you will reach an intermediate group before reaching the group that hosts your destination. So, assuming now perfect adaptive routing here, we will here have an oversubscription or a blocking of two. So, in order to have this, to achieve this kind of oversubscription, it's recommended to stick to I would say a balance criterion or a ratio here that, okay, to say something wrong, that A should have twice the size of P as well as twice the size of H, according to the definition of the Dragonfly. And that's because of to balance then the ratio between global and local traffic. Let me also show you a construction example. Assume now that we have switches of 16 ports, and the question is, what would be the maximum or the largest Dragonfly way we can construct by those switches? We have the building block here, our 16-port switch, assumed to be 16 ports. And that means now that A will have the value of 8, and P and H will have the value of 4. So recall now that according to the definition of the Dragonfly, each group will consist of 8 switches, which in our case now is 8. So we will have this group. And each group will then also have 32 terminals connected to it, which is just A multiplied with P, and the same number of global links. Then a number of those groups will then make up the complete tree. More precisely, the entire network will consist of 33 groups, which is just computed by this formula, and the number of switches in total will be 264, and the network will consist of 1,056 terminals. And as already said, there is a full connection between the groups, so just illustrated by this mesh pattern here. Now let's talk a bit about the topology inside the groups, and the guys behind the Dragonfly recommend a flattened butterfly, and here we have just illustrated a one-dimensional flattened butterfly. That consists of 8 terminals as well as 8 external connections. So as you can see, it's fully connected. So each of them has a connection to each of the other switches in the group. But still, non-minimal adaptive routing has to be used here for path diversity and for load balancing. Just bear that in mind. So you need both non-minimal adaptive routing both at the global and the local level here. Now, what about the fat tree? Could that also be applied as a group topology? Yes, the answer is definitely yes. So, for instance, possibly the spare links at the root level, the top level, could be used for connecting the global links. So basically, there are two options for using the factory also as a group topology in the Dragonfly. One option is then to connect the global links to the bottom level of the factory. So here we have a group here in the factory that is made up of a two-level factory, and then you just hook up to the other groups from the bottom level of the factory. And the other option is then to, as already said, is then to hook up to the other groups or connect the global links to the topmost level of the factory. But those two different options may or slightly give the resulting Dragonfly different properties, as we can see a bit later. Okay. Then to the scalability and cost issues. As Noah just said, both flattened butterfly and the factory are viable Dragonfly group topologies. And we have compared those three configurations with a regular 3-level and 4-level factory. And we have looked then at how the blocking and cost of those topologies develop as the size increases. Let me also mention that we have derived equations here that describe the worst case blocking characteristics of these topologies. So input to these equations will, for instance, be the size of the switches and other design parameters, and also, for instance, also that we could use parallelinks between switches at each level in the factory, and also at the global and local level also for the Dragonfly. So we test almost every possible value of the design parameters and explore the entire solution space for these topologies, looking for the most cost-efficient solution, at least how they develop. So about how do we compute the cost? Well, it's quite simple. It's just the number of integrated circuits or chassis, plus the number of switches, plus the number of short links, and plus the number of long links, where each of them is then just multiplied with their element cost. And about the element cost, which is then has a normalized value, and the cost of short links is 1. The cost of long links is 3.75, and the cost of switches is 62.5. And for the integrated switches, it's this cost is made up, or is simply the number of switches that make up this chassis multiplied with 1.5. And those cost ratios are simply based on the prices commonly available for InfiniBand hardware. Okay, then we're coming to the essence, the results, and let us first focus on when the topologies are built from 36-port switches. And what we have here is the normalized price per terminal or per host as a function of the number of hosts. And we will also differentiate it or divide it into different blocking ratios as seen up here. So here we have 4, actually color-coded here. So here we have 4 intervals here. We have the red one that defines the blocking ratio below 1.1. Well, in practice that is non-blocking. But note that the factories will always have for this interval will always have a blocking of 1.0. But the Dragonfly variants, they also have a bit higher here that varies a bit up to 1.09. And we then also open up for increased blocking here, for given by those three other intervals here. Even we go up to allowing for a blocking up to 4. Let's then look at the results, and let's start then for the non-blocking case, the red interval, and let's first then look at the Dragonfly, when using the flattened butterfly as the group topology, and it scales like this. It scales up to around 25,000 terminals. Let's then introduce the 3-level factory. We see the cost is quite constant. It doesn't scale that a bit less than the Dragonfly. But note here now that the cost of the 3-level factory is in average 5 times less than the Dragonfly. I should have said that the axis here are in a logarithmic scale here. Okay, let us then next introduce the Dragonfly, where we've been using the factory as the group topology, and with the global links are connected to the bottom level, and that behaves like this. And then next we have the Dragonfly, also made up of using the factory as the group topology, but remember now connecting the global links to the top level, and it has a behavior like this. What do we see here? Well, we see that those Dragonfly variants scales further up. It scales higher than the Dragonfly made up of the flattened butterfly. But we also see that the cost here varies, and that's simply because they are quite sensitive to the parameter configurations. There are some parameters that are more optimal than the others. Finally, let us then introduce the 4-level factory. We see the cost of it is completely constant, but we also see it scales quite far beyond the scalability of the Dragonflies. Actually, it beats them with several 100,000 terminals. But note also that beyond the scalability of the 3-level factory, we see that there are some intervals or cases where the cost efficiency of the Dragonflies here are better or less than the 4-level factory. Okay, let's now open up for increased blocking. What do we see then? Well, we see that the networks can continue to increase in size, and particularly that's true for the factories. And we also see that the price then drops significantly. So what is the main conclusion that can be drawn here? Well, I would say that the general conclusion here is that the factory is far more scalable and more scalable, and it's actually a better topology than the Dragonfly. And but there are some cases here where the Dragonfly is more cost efficient. Well, we also computed the results when the networks are built from 48-port switches, a bit more looking into the future. But the picture and the trend is completely the same as we can see here. That we have there we have the Dragonfly when it's made up of or the group is the flattened butterfly. Then we have the 3-level factory and so on. The picture is entirely the same. The only difference is that the networks grow to a much, much larger size. Actually, the 4-level fat tree here is, for the non-blocking case, is actually approaching 1 million terminals. And now open up also for increased blocking. For sure, the networks can increase significantly in size. And in fact, the 4-level fat tree here can consist of several millions of terminals. So here we really talk about huge configurations. Okay, that was more the worst case analysis we have done, but based on the derived equations. But we have also studied or looked into what is the average blocking characteristics of the Dragonfly when adhering to this balancing criterion where A should be of twice the size of P and H. The way we have done this is that we have developed or implemented an algorithm that optimally allocates the paths for a given permutations of the nodes. And we have collected statistics for 100 random permutations. I always say it's a sufficient high number. And we've done it for the maximum size Dragonfly that can be built of 36 port switches. And this consists of more than 25,000 terminals. And this figure here, it shows the load distribution of the global links. And the average number here is, or the average load is 1.53. But we see also that a significant portion of the links have a load of 2.0. But the average number, this is the average number. Okay, let's then look at the load distribution of the local links. And the average number here is 1.69. But we also see that there are some links that have the load 3. Consisting of 3 flows or paths here. That was more or less all what I had, so it's just then to conclude. And okay, when comparing the Dragonfly topology with a regular fat tree, what we see here is that the fat tree is, I would say, is superior in terms of cost efficiency, scalability and blocking ratio. But there are a few cases where the Dragonfly actually surpasses the fat tree. But that's with respect to the cost per endpoint. But you should also bear in mind that the Dragonfly supports or requires support of non-minimal adapter routing both at the global and local level, as well as it needs advanced congestion look ahead for optimal operation. And yeah, that's not supported by any hardware today. And furthermore, virtual channels or multiple virtual channels would be needed in order to avoid deadlocks here. So I think it's a fairly clear message. You can just continue with your fat trees. Yeah. So thank you for your attention, and yeah, maybe there will be some questions or.